So in the ligand field theory model here, we're going to think about making molecular orbitals from the combination of atomic orbitals on the metal and on the ligands. So to get started, if we're interested in the orbitals on the metal, then those are going to be the d orbitals, so the 3d orbitals, and those are going to be the 4s orbital, or 5s or whatever, and the p orbitals. And we know from our character tables that in the octahedral point group, because that's what we care about, the 3d orbitals are divided into an EG group and a T2g group. We know that the s orbital is going to be the totally symmetric representation, which in the octahedral point group is A1g. And we know that the 4p orbitals are going to have the same symmetry as XYZ, so that's going to be T1u. Now, in order to do the ligand orbitals, we're going to need to think of them as a group. So we're going to generate a reducible representation for some group orbitals. So for the group orbitals, we can come over here. All right, so we're going to think about our octahedron looking kind of like this. And we got our ligands. And we're interested in the sigma bonding first. So we're thinking about like orbitals on the ligands that are pointed directly at the metal. Or another way you could think of it is like you have an arrow that's pointed at the metal. Kind of like that. Or again, we're thinking about like these little lobes of orbitals that are pointed at the metal. And there are 6 of them. Okay, so we're imagining that's our basis that we're thinking about. Okay, so we're in the octahedral point group, OH, and let's think about each of the symmetry operations there. We have E, we have 8 C3s, we have 6 C2s, we've got 6 C4s, a lot of operations here. 6 C4, we've got 3 C2s, which are going to be equal to the C4, so the C2 along the C4. We've got inversion, 6 S4s, 8 S6s, 3 sigma H's, and 6 sigma D's. And remember, a sigma D is just like a sigma V, but in this point group it's called a sigma D. Okay, so we're going to think about the group of ligands to make our reducible representation. So if we do the identity operation, pick it up, put it down, then all 6 of those ligands stay pointed in the same direction. If we do the C3, then that doesn't pass through any of the ligands, so 0 of them are going to remain unchanged. If we do the C2, then then 0 of those are going to remain unchanged. So that's going to be the C2 that's like between the bonds. If we do the C4, then the ones that are along the C4 axis, those are going to stay the same, but everything else is going to move, so 2 of them. If we do the C2 that goes along the same as the C4, so this is the one that's through the bonds, then in that case, 2 of them are going to stay the same. If we invert through the center, everybody moves. If we do the S4, so rotate 90 degrees, and then delta H. So the C4 left 2 of them in the same place, but then if you do the sigma H, then everybody moves. If you do the S6, so that's going to be a 1/6 of a turn, and then flip, all of those move. If you do the 3 sigma H, so you're going through the equatorial plane, then 4 of the ligands are going to remain unchanged. And if you do sigma D between the bonds, then that'll go through 2 of the atoms, and so 2 of them will remain unchanged. Okay, so there is our reducible representation for sigma bonding in an octahedral transition metal complex. If you reduce that using your reduction formula, then you're going to get a group of A1G plus T1U plus EG. And so then those are going to be our ligand orbitals over on the other side of our diagram. And we're going to imagine that the ligands are more electronegative than the metals. So we're going to put those 6 ligand orbitals over here. So we said there's an EG and a T1U and an Ag set. Okay, so on our diagram here, we got the left side is the metal, the right side is the ligands, and in the middle we'll make the metal ligand complex. Okay, so let's think about what matches up here. We've got the EGs will make a bonding anti-bonding combination with the other EGs. So we'll have an EG bonding and an EG, oh, I made that a little bit too high. I'm going to bring this one down. We'll have an EG bonding and an EG antibonding. We'll have AG bonding and antibonding, and it turns out that the AG orbitals are actually a little bit lower than the EG orbitals, and remember, we're not going to fuss about really figuring those out rigorously, but, so just go with me here. So we can have AG star. And we're also going to have T1U. So there's going to be an antibonding T1U and bonding T1U. Come on, T1U. There we go. Okay, now what we have left over are the T2g metal orbitals. So they're non-bonding, so they're just going to stay at the same energy that they were. T2g. All right, so look, we have our T2g and our EG star orbitals, and look here. They have the same splitting pattern that we got from the crystal field theory. So the difference in energy between the T2g and the EG star orbitals is our delta O. Now let's think about how the electrons are going to fill here. So we're assuming that our ligand orbitals, since we're imagining those as being like Lewis bases, those are completely filled. So we've got 12 electrons there. And then the d orbitals, so we're imagining that for the metal, the s and the p orbitals are unoccupied, and we've got the d orbitals. And, they're going to be filled with however many electrons come from the metal. So if we imagine that this complex is actually, this is nickel 2+, and these are water ligands, maybe that helps you a little bit. So then we're going to have 8 electrons coming from the metal. Now, okay, let's fill in these orbitals. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's all the ligand electrons. And now we can think about the number of metal electrons is just going to, in these T2g and EG star orbitals, is just going to depend on the d electron count of the transition metal. So here, that's going to be the 8 electrons from nickel 2+. So the take-home message here is that whether we use crystal field theory or ligand field theory to think about sigma bonding, we're getting kind of the same picture. In the next slide, we're going to think about how it changes when we introduce pi bonding.